We're going to look at our questions 1 to 10 from the multiple choice, all about momentum and impulse, etc. Let's get started. Okay, we've got two blocks of masses m and 2m respectively, and they're traveling at constant speeds but opposite directions. Total momentum of the system before and after the collision. We can already rule out a couple of answers here because we need to apply our conservation of momentum here. The momentum before should equal the momentum after. So we're really left with two choices, A and D, because those are the only ones that show the same expression on those in the row. Okay, if we look at our total momentum, well, the way to do so is to add together the momentum of body 1 and body 2. Now I've put that in as m1u1 plus m2u2, u representing the initial velocity here. We can see here that m1 is double m2, and their velocities are the same but opposite, and so therefore I've got a positive v here and a negative v on the other side. We're then left with 2mv plus minus mv, which then leaves me with mv, and so therefore my answer here is A, because the total momentum before should be the total momentum after. We're assuming, obviously, there are no external forces acting here as well. Let's have a look at this question. This is one with a lot of content in here. We have to take our momentum and then apply it directly to our projectiles question. Let's take a second to read it. We've got two balls of the same diameter with the same momentum. However, the mass of x is greater than the mass of y. Why is that important? Well, if they've got the same momentum and different mass, this means we're going to have different velocities. And remembering that at the beginning of this process, they're being fired horizontally, so they are moving horizontally. What this really means is that their horizontal velocities are going to be different. And in this case, the horizontal velocity of x is going to be lower than the horizontal velocity of y. Therefore, the horizontal distance is going to be different too, which means we can look at answers C and D. We can get rid of A and B because that's saying that the distances horizontally are the same. We now need to apply suvat. We know that we are traveling from the same height, so that's the same displacement. We have the same acceleration. We have the same initial velocity in the vertical direction, which is 0. According to suvat, time must be the same as well. And so therefore our answer here is C. Here we've split up the velocities in terms of their horizontal and vertical directions, and then compared them and compared the mass in getting that central point that the initial horizontal velocity is less for x than it is for y. Question number 3. I think we're going to take this one, we're going to take each statement in turn. We've got which statement is true for an object traveling in a straight line at constant speed or constant velocity. A, no forces act on the object. Well, we're aware that actually things may be acting on the object. However, what the statement here is that the forces are balanced, i.e. there is no change in the momentum. Careful with number C, the change in the momentum is 0. However, the object is moving, and so therefore its momentum is non-zero. And as for A, if there are balanced forces, there may both be doing work. However, the net work is 0. In other words, the two forces are working against one another. Okay, we may have a driving force and a friction force, which are pushing against each other. Both forces are doing work. However, the net work is 0. This does not mean that no work is being done. It means that the two forces are cancelling each other out. So we're left with B. The momentum is not changing, which means that there is no resultant force. Remember, our momentum has a direction and a value, a magnitude. If we are moving in a straight line at a constant speed, that means our direction is the same, as is our speed, as is our velocity. So we are not changing our momentum. Stone is thrown vertically upwards from the surface of the earth. Which of the following quantities will not become 0? I suggest you look at the ball at the top of its trajectory, because this will make your question very easy. We know that at the top of the path, the speed will be 0. That's because we stop and we're turning around and we're just about to start heading down again. If the speed is 0, then the velocity is also 0 at that point. because remember, our velocity is essentially the same as the speed, it just has a direction. Now, momentum is the product of mass and velocity, which means that if the velocity is 0, the momentum is also 0. So by process of elimination, we're left with d. Well, why is d the answer here? Well, when we're being thrown in the air, the acceleration is always equal to the gravitational acceleration. In other words, it is never 0. And so therefore, the answer here is d. Body moves in a straight line. We've got a force F acting on the body and a resistive force, small f. Both forces act along the same line, but they're in opposite directions. The rate of change in momentum, well, that's our Newton's second law. Force is the rate of change in momentum, but here we're looking for the net force. In other words, the sum of these two forces, the resultant. Our resistive and driving forces are in the opposite direction. I'll take the driving force as capital F in the positive direction and the resistive force in the opposite direction. We're left, therefore, with the resultant force being F minus F, which is delta P over T. That's the rate of change of the body, momentum of the body. In other words, our answer here is 1, or A. Which following is a correct statement of Newton's second law of momentum? Well, we've just had it there, that we have the rate of change of momentum is equal to the resultant force, or the net external force on our body. In other words, force net is equal to delta P over delta T, and so therefore this is B. We look at A, C, and D. A, absolutely, the force is proportional to the mass in the body. However, it's also proportional to the change in the velocity as well, the rate of change to the velocity. The momentum of the body is proportional to the net external force. No, we're looking at the change of momentum. That's two separate concepts there. Force acting on a body is proportional to the acceleration. It is proportional to the acceleration. However, it is with a more formal way of expressing that is to include the momentum in our answer. Two identical spheres, each of mass m and speed v, travel towards each other. Again, we're told the speed but not the velocity. Okay. Now, let's have a think here. They undergo a head-on-head elastic collision. Let's go through our statements again. Let's have a think about the total momentum here. We've got plus mv here. Why is it plus? Because we're moving to the right. We've got minus mv here because we're moving to the left. mv minus mv is 0. Okay, and so therefore, after the collision, as long as we have no external forces, the total momentum of the spheres should not be 2mv, but equal to 0. Before and after the collision, the total momentum is conserved, and so therefore we must have the same momentum before and after. Let's have a look at B. We've got an elastic collision, and therefore we're expecting these spheres to have some kinetic energy. If they have kinetic energy, they certainly do not have 0 momentum, and so therefore that answer is ruled out. Total kinetic energy of the spheres is mv squared. Well, we're told at the beginning that it's elastic, so we can calculate the kinetic energy at the beginning and then compare it with the kinetic energy at the end, and they must be the same. Here we've got a half mv squared, and we've got a half mv squared. Well, a half plus a half gives me a whole. We've got half mv squared plus half mv squared gives me mv squared. That is the total energy initially, the total kinetic energy initially, I should be specific. Well, that must be the final. So our answer we expect here to be C. Each sphere has 0 kinetic energy. Well, again, we've said that the spheres, if this is true, then the kinetic energy is not conserved. If we had 0 kinetic energy, that would mean we'd gone from a situation of kinetic energy to 0 kinetic energy, in which case this would be an inelastic collision, which is why the answer here is C. Difficult one, this one, and it actually requires a little bit of understanding on our future topic of gases. Okay, the answer here is C, and the reason here is because this is a crucial assumption in the kinetic theory of gases. Okay, let's just break this down a little bit. We should be aware that whenever we have two objects linking together, so in the case of B and D, those are inelastic collisions because there's always some kinetic energy lost. In the case of that was A and D. In the case of B, it may be tempting to say that the two railway trucks colliding and the two gas molecules are the same. However, we're really looking for this idea of changing direction, and both of them must change their direction in order for this elastic collision to occur. If they do not necessarily change direction, then we cannot guarantee that it is an elastic collision. Again, another very tricky one because it requires a lot of thinking here. Okay, we'll go through the statements and try and rule them out. Okay, we've got a child throwing a ball to child Y. The system consists of the ball, the children, and the earth. What is true for the system when the ball has been caught by Y? Okay, first one, well, A, the momentum of child Y is equal and opposite to the momentum of child X. You may be tempted by this one because there's a transfer of momentum between the two. However, we have to remember that child Y is also holding the ball when he catches it. And so therefore, when we're thinking about the transfer of momentum between the two, then we need to include the ball with the child X as he's holding it. Okay, there are other things going on here as well. However, if we're looking at a simplified picture, child X gives P to the ball, and then the ball is caught by child Y. When the child Y catches the ball and child Y's momentum must also be Y. Now, must also be P. Speed of rotation of the Earth will have changed. Well, we have technically this is true. There will be forces on the Earth which cause it to rotate at a slightly different speed. However, the friction forces are equal and opposite between the two children's sets of feet. And so if child X, for example, is rotating the Earth in one direction, child Y will rotate it in the other direction, and those effects will cancel out. It's clear, I hope, from part C that the ball is moving, and so that means it has momentum, and so therefore this no net momentum does not quite make sense. And lastly, the total momentum of the system is not changed, and this is always applicable to closed system, which is why the answer here is D. Okay, sometimes when you're looking at these questions very detailed, actually we have to take a step back to remember actually that when we've got our momentum of our systems, our Earth, our ball, and the two children, all we have to do to work out what's going there is to apply our conservation momentum, and so therefore to remember that the total momentum of the system has not changed, providing there are no external forces here. Last one, slightly nicer. We've got a moving system undergoing an explosion, and we want to know about the momentum of the system and the kinetic energy of the system. In an explosion, we have an initially moving system, okay, and that what we find is that because of the motion of our particles after an explosion, we find that the kinetic energy increases. Okay. However, when we began the situation, we kind of had a case where we had zero momentum. Okay, in terms of the internal parts. Okay, and in that case, the momentum is conserved unless an external force acts. Okay, so despite the fact that the system was moving in the first place, its momentum must always be conserved, assuming that we have got no external forces. Okay, the kinetic energy increases because the moving parts within that system are moving more. We have non-zero momentum, and therefore the kinetic energy has increased, and therefore our answer here is A.